is last session this afternoon. It gives me a great pleasure to introduce Pavao Mardesic from the University of Bourgogne. He will speak about the displacement functions for deformations of Hamiltonian. And in some sense, Pavao has been collaborating with Mexico for the last 20 years at least, and he has come here at least half a dozen times, so thank you very much.
Thank you, Javier. So, yes, I think that in some sense I feel Mexican. I'm Croatian, French, and kind of, I think that you have adopted me as a, as a Mexican. So I'm here as, like Mark, as a predecessor of the creation of this UME. And first of all, so I'm here in Mexico since September. And first of all, I would like to thank Pepe, whose idea it was. He invited me to come here. So we have some pending work, which unfortunately, as it is always in research, somehow one has to make some choices. There were other things which were working very well, which I will present you, and so we didn't have time somehow to work on it. But now that this UME exists, I will be very happy to come back and to work on what we started. I would also like to thank very, very much to Laura, with whom, so she is here, who somehow received me very well in Mexico. It was a great pleasure to work with her. She shared her office with me, and we worked together on a daily basis. And I think there is, so the English word is affection, but I think cariño is much more appropriate for somehow the relationship which we have. And finally, I want to thank Javier. He's somehow the beginning of my Mexican connection. I just checked yesterday and was very happy to see. So we have 5 papers in common, which makes Javier one of my first collaborators. And I am very proud that I saw that I am also Javier's one of the first collaborators. Okay, so the work is really a work hecho in Mexico. So 4 authors. Let me somehow explain the structure. So Laura and I co-directed the thesis of a Mexican girl, Jessie Montigo Herrera, who defended her thesis in Mexico a year ago. Javier was also, and Pepe in the jury. And she's now postdoc in the Weizmann Institute in Israel. And so this is kind of, they came here, they spent some 2 weeks more or less in Mexico where we're working together. And also we have regular Skype meetings, and I mean, it's really we are very happy about the work. So let me explain what we are studying. So we are studying vector fields in the plane. I start with motivation. Motivation is in R2. So you have, so these are polynomial. So we have a field of vectors. I like to see vectors like grass, which somehow from every point we have a vector. And then we have, this is the vector field X. And then we have, of course, to it is associated its trajectories, which are somehow the speed of these vector fields, trajectories. And in the plane, there is not much space for some complicated dynamics. But essentially, there are 2 things that can, there is one thing that is interesting. And this thing is periodic orbits. So periodic orbits. So it's a closed orbit, something like this. And there are 2 types of periodic orbits. So periodic orbit can be isolated or non-isolated. Isolated means that nearby orbits are not periodic. We have, kind of spirals. And non-isolated is a situation somehow like this. When speaking about these trajectories, it will be somehow more convenient. So we have a vector field, which is, say, PQ, and it will be more convenient to use the language of forms and take the dual form, which is dq q dx minus p dy. Here, of course, p and q are polynomials. Okay, so with these two problems, we do these two. Oh, okay, maybe I just give us an example of a non-isolated orbit. If you take a polynomial f in R2, R of xy, with isolated singular point, then isolated extremal point. Then we have a picture like this for the form df is equal to 0. Okay, what I wanted to say, so there are two problems associated to these two cases. On one hand, we have the 16th Hilbert problem. And on the other hand, we have a center problem. So 16th Hilbert problem, it is the problem to bound the number of, so these isolated periodic orbits are called limit cycles. So bound the number of limit cycles in function of degree of the vector field X. So this is one famous problem which is open for more than 100 years. And on the other hand, another famous problem is the Poincaré center problem. So it is characterized, so this is the center problem. So it's characterized non-isolated periodic orbits. Why is it called center problem? Because normally in the middle you have a center. It's not necessary, but usually is the case. Okay, so this problem also is completely open. It is solved in a good way only for quadratic vector fields since Dulac. Each one of these problems, it is kind of a vague formulation. So you have a center, you have a situation like this, and you want to understand why. For instance, one reason is you can have precisely like here, the example df equal to 0, but there are cases where you can have such a picture by symmetry. If you have something that locally could be a focus or a center, but you know that it is symmetric, then necessarily it is a center. So this is kind of one other way how it can happen. And then there are other ways, and the question is, give a complete list of reasons why something is a center. Okay, now what we look at is a deformation. Let us take df plus epsilon omega equal to 0. So this is deformation, which appears in the title. And now the question is, each one of these problems has a counterpart for deformation, which is I attribute to Arnold. So clearly, for the 16th Hilbert problem, it was clearly formulated by Arnold. I don't know if it was really formulated in the other case, but it can be considered. So the question is, you take f, you take omega, you fix just the degree, and so for epsilon equals 0, there are no limit cycles, because we have a picture like this. We don't have isolated periodic orbits. We deform, and then the question is, bound the number of cycles of limit cycles, sorry, that are born. So this is called the infinitesimal 16th Hilbert problem. I will write it here. F is polynomial. If f is 0, then there are no. You fix a degree. You say degree is at most 5. How many limit cycles can be born? If maybe no.
If f is 0, that means that it's a standard.
Ah, okay. Okay, I understand. Yeah, so f has to be non-degenerate. Essentially, the idea is that you start with a picture having a center. You start with a picture having a center. You deform a center, and you look how many limit cycles can be created by deforming a center. Okay, and there is also infinitesimal center problem, which is characterized omega such that f such that so this deformation df plus epsilon omega equals 0 preserves the periodic orbits. What do I mean by it preserves the periodic orbits? Of course, the periodic orbits will move, but we still have a continuous family of periodic orbits. So this is somehow the motivation for our research, and what is kind of how does one tackle these kind of problems. So what one does is one considers the displacement function. So what is the displacement function? One takes a transversal. So in any of the two cases, you take a transversal, and you look at the first return. So what it is the first return map minus identity. So displacement I will make a new picture. So you take a transversal, you have your cycle, and then after deformation, you have something like this. Start here. And so this is the displacement function, how much you moved when you came back. Okay, and so this displacement function has two problems. Yes, okay, so each one of these problems corresponds to the first one, corresponds to the problem to bound the number of isolated zeros. So this is infinitesimal Hilbert 16 problem. And the other one is characterized when characterized deformations such that delta is identically equal to 0. So what is known? Okay, so we have a function delta which depends on two variables. One is this transversal variable, which I will note by h, and the other is the parameter of deformation, epsilon. Of course, all this depends also on omega. And at some regular point, one can write it as some mi of h epsilon I. I goes from 1 to infinity. So these functions are called Melnikov functions. What is known? So there is an algorithm how to calculate these functions. So this is an algorithm, I would say, which is due to Françoise and Gavrilov, the theorem. So these are the Melnikov functions, and we denote by m mu the first non-zero Melnikov function. So the theorem is that m mu is an iterated integral. I didn't write, so this is Françoise and Gavrilov. Is an iterated integral of length mu. What does it mean? So I will write just the first few cases. M1 is integral along gamma. Gamma is a family of cycles that that appear here. So actually M1 is an abelian integral. M2 is the integral of omega prime omega along gamma. So this is an iterated integral where omega prime is the Gelfand-Larrey derivative, so it is d omega divided by df. So you take a one form omega, you take d omega, it is a two form, you divide it by df and you obtain a one form. So there are here two one forms. And what does this mean? This is a notation which is iterated integral. So you first take the primitive along gamma of omega prime, and you get the function, and you integrate it, you multiply by omega, and then you integrate along the closed curve gamma, and so on. The problem is that this theorem gives that m mu depends on mu. And we want it depends on the deformation omega. And we want a universal bound for the length of iterated integral m mu.
So this m1 is a function of h?
m1 is a function of h, yes. So here it is h and here is h. Same thing for the other ones. So gamma h, of course, is a subset of f minus 1 of h. So why is it important to have such a universal bound for the length of mu? It is important for the two problems. So if we want to have a uniform bound for the number of isolated zeros, we must know what is somehow the complexity of our displacement function. We have to have a priori knowledge bounding the complexity of this function. And as far as the center problem, infinitesimal center problem is concerned, so one approach is that, of course, you must annihilate M1, M2, M3, M4 by the netter property. It stabilizes, but you don't know when. And so this is kind of replaces the problem. It is, I would say, an important step forward for both of these problems. So what we want. And so there are examples where the length of the first non-zero Melnikov function is much lower than this mu. So theorem Ilyashenko and Françoise. The theorem doesn't appear, but you can deduce it from their work. Putting together their results is for generic f, m mu is of length 1. This means that it is an abelian integral. Note that in the theorem I never supposed, I didn't put any hypothesis on the deformation. It is for any deformation omega, the hypothesis is only on f.
Is it something that you can test on F? Or?
It is something that you have to, so here it is very explicit. It's what you think in this case. This theorem was generalized by Gavrilov and Ilyev. They gave a criteria for m mu to be of length 1. So it is more general than the hypothesis. In our work, so I had a student from Chile, Marco Uribe, who showed that in the case where f is a product of lines, one gets that m mu is of length 2 at most. And it was essentially generalized in the thesis of Jesse. And so this somehow motivated our work. And let me now just state the result. So theorem so we define, okay, let's see. So this is Novikov, Pontigo, Ortiz, and myself. So for any deformation, df plus epsilon omega equal to 0 of df equal to 0. The first non-zero Melnikov function m mu is an iterated integral of length kappa kappa equal kappa of f gamma. So this is the first statement. I will say just after what is this kappa. And the second statement, 2 if kappa is bigger than 1, then there exists a deformation omega such that m mu is not of length 1. So this second part is an exact converse of the theorem of Gavrilov-Mendeleev. So Gavrilov-Mendeleev give a condition assuring that one gets an abelian integral, and we show that their condition is good, that this is the good condition. And in the 30 seconds which remain, I will try to define the function k of this function k. So essentially, so definition of kappa, sorry. So first thing, one complexifies. So we consider f as a function from C2 to C. And then we have monodromy. So the cycle, we had a real picture like this, a real gamma, which we plug into C2. And then we move it. So this defines when one takes out singular fibers, one gets a fibration. I don't pretend that this is a fibration. There is a subset which is a fibration. And this gives a monodromy. And then one denotes by O the orbit of monodromy. More precisely, it is we call it orbit of monodromy. Actually, it is a normal subgroup of the first fundamental group of the fiber, of a generic fiber, f minus 1 of T0 at some base point P0. Then we define a group K, which is the commutator of O with pi 1. We take commutators, and then we look at the lower central sequence L1, which is equal to pi 1, which contains L2, which contains L3, with Li plus 1 is Li commutator with L1. And then the definition of kappa. So this is the minimum of, so kappa is the minimum of j bigger than or equal to 1, such that orbit intersection to L j plus 1 belongs to this K. And essentially, we believe that kappa is the optimal bound. So let me just explain somehow the idea. The idea is that, the only thing that is important is the orbit. This K is somehow something that we kill. It is killed in the problem. And you look at commutators which are bigger and bigger, longer and longer commutators, until one arrives to this K. And when one arrives to this k, the minimum of such numbers, so we haven't been able to prove that this set is non-empty, but we are quite convinced that it is the case. And in all the examples that we know, it is the case. And this theorem actually, it contains the theorem of Ilyashenko-Françoise. It contains the theorem of Gavrilo-Ilyev, and the thesis of my student Marco Uribe, and somehow the generalizations that have been done, so in the co-direction of Laura and me, of Jesse, for some more complicated cases. I think my time is up, so I have to stop.
Questions?
Yes.
I don't know if it's a question or comment. I'm really surprised about how all this, the definition of this constant kappa, why this commutator show. I don't know if it has a relation. There's something called chain.
Yes. Yes, it is. I mean, I of course have no time to so the integrals. When I say iterated integrals, it is chain iterated integrals. All these iterated integrals are chain iterated integrals. So they play, and a key ingredient of the proof is an isomorphism given by chain, which is based on chain iterated integrals. So I mean, your remark is very. I didn't ask you to make the remark, but I'm very happy that you that you made it.
Any other question? So a polynomial function is like a rational function which has some behavior at infinity. Could you extend these kind of results for rational functions?
I think so. Yes, I think it is
Same.
same. Yes.
Okay. We thank all of you.